Hello everyone and welcome back to another lecture for machine learning techniques. This is the lecture number 6 and today we are going to look into Gaussian models. So far we have looked into all your logistic regression and SVM decision trees, which we will be looking into, and how to separate classes, or how to distinguish, or rather how to discriminate. Now, instead of trying to separate them or trying to find the border through which you can find two different classes, what if you can learn the characteristics of a particular class based off its data distribution, and then based off that try to assign labels to a new data point? So today we're going to look into the generative models which tell us how to do this, and also about MLE, GMM, and the EM algorithm. So let's start with generative versus discriminative models. What is a discriminative model? That's what we've been talking about, so far. All your logistic regression, your decision trees, how to find the line to separate two different classes. Now, generative models will try to find the discrimination or the distribution of a particular data, or the class within the data. Either it can be the shape or the population density or any common traits. So for this, we have the naive-Bayes algorithm and the Gaussian models, which are very popular generative models. So what is this Gaussian distribution? We are always in this curve. It's a Gaussian or a normal distribution. So basically, it's a probability distribution that describes many natural phenomena. You see anywhere in nature, almost any number or lots of continuous or even discrete data values are going to follow a normal distribution or a Gaussian distribution. Very simple. Just take your exam marks. You'll see a lot of people are hitting the average. There are a few people who are exceptional, your toppers. And a few people who do not pay attention to class who are going to get less marks. But most of them are going to be around the mean or the average. So here, what is it that we are looking at? We want the mean and we want the variance. How much spread is there away from the mean? So these are the two major parameters for a Gaussian model. So now, what is this MLE? We talked about your mean and your variance. So how do you find? How do you estimate? So for that, we have your maximum likelihood estimation, which is the likelihood or the maximum likelihood of a particular value being the mean, or a particular value being the variance of that particular distribution. Very simple. Let's look at, let's say that this is the distribution that you have. These are the marks in your exam, and you've put it into a simple histogram plot. A lot of people are getting the average mark, few people high, few people low. So it forms a Gaussian distribution. You can form multiple different Gaussian distributions, but what is the one that fits the best? This is the one, say the one in green, which is the one that fits the best. Why is this so? Because this one gives you the highest MLE, or is the highest maximum likelihood estimate of your particular mean and your particular variance for that particular data distribution of your marks. So what is math behind MLE? I know this may look very complex and very big, but you just need to understand how it generally works. So, you're just trying to find the likelihood, or what is the probability of a particular number being the estimation for a particular distribution. So in plain English, the probability of seeing a specific data points given, we assume the data come from a Gaussian distribution with a particular mean mu and a variance square. So the goal is to find your mean and variance and maximize your likelihood for your particular distribution. So this is your data. You have your mean, your variance, and your different points in the data. So we always take the log, because it's easier to maximize the log of a data, because whenever you look into, you take powers, you can just, it becomes into a multiplication with a constant, or if you do multiplication of x, log of xy becomes log x plus log y, and so on. So it is easier to maximize, it's easier to derive, it is easier to maximize, it is easier to scale anything to be done in the log function. So yeah, here we take the log of it and then you spread out. This is your usual Gaussian distribution, and since ln of x into y is ln x plus ln y, we split that too, and then it's an exponential with a power, and ln of e is 1, so the power becomes the constant itself, and again the power comes out, so you multiply it and so on, and then you split once again. You have 2 pi into omega square. So this will be your maximum likelihood estimate for a particular data distribution to find your MLE. So the best fitting bell curve is the one that is centered at the data's average with the data spread, where the data's average is basically your mean and your data spread is basically your variance. So we try to maximize the likelihood of your mean, and you try to maximize the likelihood of your variance for that particular data. So we have one curve. Okay, fine, we can fit the entire data distribution. But what if there are multiple different curves? For example, let's look at this analogy where you measure the heights of all the students in a university. Well, the data set includes both the general student body and the university's basketball team. So now what you will see is in a general student body, yes, there is going to be one Gaussian distribution. But in the basketball team are people who are already tall, but within them itself there's going to be another Gaussian distribution. So you will see a histogram with 2 different peaks, and you can't just fit one single Gaussian curve. So very simple. Why don't we have 2 curves or more than one curve to solve this problem? And that is what we do. This is called a Gaussian mixture model, where each is split into different distributions. As you can see, there's 1, 2, 3, 4. There are 4 different peaks, which means there are 4 different Gaussian models, which makes it a Gaussian mixture model, and each of them have their own mean, each of them have their own variance, and obviously there is something called a mixing weight. How much proportion of data or how much proportion of data belongs to that particular Gaussian distribution. So how do we fit a GMM now? This is a little bit more complex, than just fitting a single model, because you can just do a bit of trial and error. If you have a single model, you can try to, put the points, find the loss function, and optimize it. But then when we have a GMM, how do we do it? Because each and every point has to be compared across with all the different Gaussian mixture models that you have. How do we solve this? That is where your EM algorithm or your expectation maximization algorithm comes into place, which is basically split into 2 different steps. As the name says itself, one is an expectation step and another is the maximization step. It's an iterative process basically. So first we initialize, we just make random values of mean, variance, and your mixing weight value for all your different data points. Your expectation step is the E step or the guessing step. For each and every data point, you calculate the probability that belongs to each of a components. So basically, you have 3 different mixture models. For each and every data point, you check, whether it belongs to A, whether it belongs to B, or whether it belongs to C. So this is a soft assignment. Next, we have the maximization step. Once you recalculate it using the probability from the E step as weights, you try to assign what are the actual mean and standard deviation and the weights for each and every data point within the distribution. So now we are basically maximizing the parameters with respect to the steps. It is an iterative algorithm. So it was E, M, and we constantly do it, until you're happy enough where the parameters stop changing, where your parameters obviously are your mean, variance, and your mixing weight. So once you see that there's very less amount of difference with each and every iteration, you stop it. So this is a very interesting graph, on how EM algorithm works, where you have your actual data and you try to fit it. As you can see, You have an E step, you have your M step, and these are your different parameters. And as it goes, it starts fitting to data slowly. And once it is there, it is going to repeat again and again, and that is where you have to stop your algorithm. So see, your E step moves the within the graph, whereas M step moves the graph itself. That is what it does. See, E guesses within the graph where it's D, and M moves the graph itself to tell you how close we have to be to the actual parameters. Hope you can understand based off this. It's a very good image visualization. So yeah, from a 2D perspective, this is how it works. See, you have two different classes. You can see for both classes, data is centered at different points. So slowly, based on the EM algorithm, the red and yellow, as closer you go, that is where your mean lies, and you try to keep the variance of all points within. So what is the mathematics behind the EM algorithm? Yes, it's a bit complex, but it's fine. Just for knowledge point of view, you people have to understand. We are basically trying to maximize the expectation, or trying to maximize the average. And again, since we told always log is easier to do, we try to find, and we're trying to maximize the parameters. So it's an argmax of the log of the probability of x and z. And in E step, we try to find the expectation. We try to find with respect to the distribution, whereas in the M step, we try to actually update the parameter itself. So where is this GMM used? When you want to cluster, k-means have very hard or only circular clusters. They are very limited to that particular form of data distribution, whereas GMMs create soft, probabilistic, and elliptical clusters, which are rich and which is actually what we see in real life. And anomaly detection, we can set a particular distribution of how things are supposed to work, and you see something that does not follow the general distribution, it is an anomaly, and you can flag it saying it's an outlier, or it's a problem with any device working on the data is not collected properly if it happens again and again. Or even density estimation. We saw in an example earlier where you have two different classes and you try to find where the density of that particular class is very deep in, just based off the mean. So, basic summary. What is a generative model? It's a model that turns the story or the distribution of the data. MLE is how we find the best parameters by maximizing the data probability. GMM is a mix of several Gaussian distributions for modeling complex data or multi-label data. And EM algorithm is how we fit a GMM to the actual data based off the guess and update loop to actually find the parameters and the correct values of the parameters itself. Thank you, and see you all in the next lecture.